Okay, so here we have an energy reservoir with a temperature of 300 Kelvin and 100 kilojoules of heat is transferred into the energy reservoir. We want to determine what is the resulting change in entropy of the reservoir. So we'll start off, we'll just set this problem up, define the system. Here we're looking at specifically an energy reservoir. And an energy reservoir is an example of a closed system. There's no mass transfer, just heat transfer into or out of an energy reservoir. So for the sketch, we can just do a simple engineering sketch here. We have some energy reservoir at temperature 300 Kelvin, and we have a heat transfer of 100 kilojoules into the energy reservoir. For the conditions, nothing really jumps out as far as the conditions go with the problem statement. So the main thing that we want to keep in mind with an energy reservoir is that an energy reservoir is isothermal heat transfer. So anytime we have heat transfer with an energy reservoir, it's going to be an isothermal heat transfer. Alright, because the temperature of the energy reservoir never changes. So we do have isothermal heat transfer. For the properties, we have the temperature of the energy reservoir, and we have the heat transfer. And we're actually trying to solve for what is the resulting change in entropy. So our solution, we're going to be looking for change in entropy, that is delta S. So what is the change in entropy of the reservoir? So for change in entropy, there's a couple ways that we can go about trying to find change in entropy. The first way we can try to find change in entropy is to look at the definition of entropy. So looking at the definition of entropy, we find that delta S is equal to integral of delta Q over T for an internally reversible process. So assuming we have an internally reversible process, and we can use this equation to calculate delta S. If we don't know whether we have an internally reversible process or not, we shouldn't use this equation. If we're unsure about how to solve this equation, we probably shouldn't try to use this equation. The only time that we would use this specific equation to solve for the entropy change is if we have what we know is an internally reversible process, and we have also a known relationship between the heat transfer and temperature. So this actually turns out to be one of those rare cases where we can use this equation, because we know that we have isothermal heat transfer, and in the notes I talked about how isothermal heat transfer is the only type of heat transfer that is internally reversible. So we have an internally reversible process. We can use this equation to calculate delta S. Since we have an isothermal process, we can pull temperature out of the equation, out of the integral, and we integrate dq, which just gives us T times, sorry, I wrote a mistake here, this is 1 over T. So we end up with the total heat transfer divided by the temperature. So this is the special case for isothermal heat transfer. We get that delta S is equal to Q over T. We talked about this in the notes briefly, and I mentioned that heat transfer with an energy reservoir is, for the most part, the only time that we use this equation, this way to calculate delta S. So delta S here is basically just Q over T. Q is 100 kilojoules. Temperature is 300 Kelvin. So we end up with delta S of 1/3 kilojoule per Kelvin. Now we want to make sure whenever we're using this equation, and Q over T is what we have, that we still follow the sign convention for Q. So Q in this case is positive because it's heat transfer into the system. So to wrap it up, if we ever have an isothermal heat transfer, then we use this equation to calculate delta S, and it pretty much gives us this result every time, Q divided by T. Really the only scenario where we want to do this and calculate delta S this way is whenever we have heat transfer into or out of an energy reservoir.